Okay, today we are going to derive the slope of a line as well as its intercept for regression. We're sticking with just a basic two variable, and actually this should be not an x1, this should be an xi. So we're going to stick with just a basic two variable setup here, one independent variable and one dependent variable for our purposes. And so we have some sort of line that that ordinary least squares regression produces, and we'll kind of get into the details of what's going on with that line and what the meaning of ordinary least squares is as we work through this. So first things first, I want to give you guys some identities. So a couple of identities here. 1 over n times the summation of xi equals x bar, the mean of x. So this is just an equation for the mean of x. So you sum up all the x observations, so all the x values, and divide by the number of observations. That's mean. So that should not be, that shouldn't be that should be no more than review. Same thing, 1 over n for the summation of, times the summation of yi equals the mean of y. Then we can manipulate these two items. So out of this we can get, we can multiply out the n and attach it to the mean such that the summation of all the x values is going to be equal to the mean times the number of observations. Same thing for the y's. So literally just the same step, yi equals y bar times n. Finally, another thing here for you is the summation of 1 equals n, and that should make sense because when we say the summation of 1 equals n, all we're saying is add 1 n times. 1 times n equals n. That's it. So nice and easy there. Last couple of things then too, real quick, I want to point out, if you have a constant term in your summation, you can just factor the constant term out. So it's the same thing as if we had 10, like the summation of 10, you could just factor out the 10 and say the summation of 1, and then that would be equivalent to saying 10n, 10 times n. So this part I'm actually going to erase, but if you want to write that down, not a bad idea, because you are going to see me factor out anything that does not have an index term as we move through this. Then finally, last piece that we're going to need is all about the residual of some squares. Recall that that is, the formula for this is sigma ei squared, and that equals the summation of yi minus y bar squared, and then, or not, I'm sorry, not y bar. I am making mistakes. The summation of the y, so it's the actual y observations minus the estimated y observations squared, and the sum of those. And then this we're going to want to call some function of beta naught, beta 1. You'll see why in a minute as I explain this. Which again, then these equal, if we expand this term out, the yi, this is just the same thing as saying the summation of yi, and the predicted yi, not the true observation. That minus is going to distribute into that formula. So when it was plus beta naught and plus beta 1, now it's minus beta naught and minus beta 1 xi squared. Now we have everything that we need to work with for this equation. So first, before jumping into what we're going to be doing with this, we want to get the reasoning behind the residual of some squares. Why is this coming up? Why are we starting with this to get to what this term beta 1 and beta naught, those terms mean? That's the big question. Well, the key is, or the giveaway is, in the name of what we're doing. What we're doing is ordinary least squares regression. And the key word there, or words there, is least squares. we want to minimize the square distances between all of our observed points and a line of best fit. So the line becomes, we make the best line if it minimizes the total square distances. And we use square distances because otherwise the points that are below the line would detract from the value as we were adding them with the points above the line. And so that becomes the issue, is that no, we have to, we want a term that incorporates the magnitude of all of the error off of the line. And so because we can conceive of the residual of some squares as as sort of like an error in the line, that this is a useful tool then in saying, okay, yes, we can minimize residual of some squares, we have the best line. Because if we have these points here, say this is the best line, and then I put a line out here, well, these distances to all these points are going to be way higher than the other line that I had. And so this line has way less errors than this line, because if all my points are kind of rolling along this, and I just put a line out here, this RSS value is going to be a lot higher. So that's the intuition behind it. So how do we do that? How do we minimize our residual of some squares? That's why I call this a function. Just saying it's a function of beta naught and beta 1, because those are our targets. Those are what we want to manipulate. Those are the parameters in the equation that we want to manipulate. And how we do this is we're going to take a partial derivative with respect to the constant and a partial derivative with respect to the slope coefficient. Then we're going to set that equal to 0, because that's how you find critical points in calculus. So if we can find critical points, and for our purposes, we're not going to do a second derivative test. Just take my word for it. It is these in fact are minimums. But anytime you take a derivative and set it equal to 0, it either has to be a minimum or it has to be a maximum. And so that's what's going to get us started. That's what's going to get us rolling here. Now, that being said, partial derivative of f, again, because we're calling the residual of some squares f, with respect to beta naught is where we want to start. And that's calculated as such. So we're going to restate this down here. Xi squared. This, we're going to first do a chain rule. So it'll be 2 sigma times yi, so this is the first step, minus beta naught minus beta 1 xi to the first power. Then we have to take we take the derivative with respect to the outside first, so we just drop the 2 out front, and then we take a derivative with respect to the inside second. So a derivative of negative beta naught to the first power becomes negative beta naught to the 0th power, which equals negative 1. And so that has to be pulled out here. We put that negative 1 out in front of that 2. And that is the derivative. So it's negative 2 times the summation of everything we had in the parentheses, but now to the first power. Then we set this equal to 0. Divide out negative 2, because we can do that. And again, bear in mind, we can factor out anything that doesn't have an index, just as I showed you before. So we can take that negative 2 out, and we can eliminate it into that 0, which is quite handy for us. Makes our lives easier. Now we're left with just this. Next thing we can do with these, with our summations, we can break them apart into individual terms. So we can distribute the summation like we would some other coefficient on the outside of a parentheses. And so this becomes sigma yi minus sigma beta naught minus, getting ahead of myself here, getting excited. Okay, sigma beta 1 xi equals 0. So now we've broken this down, and we do this exactly so we can utilize our identities. So first identity, we have this, yi equals the mean of y times n. So we're going to leverage that. Mean of y times n minus. We could factor out the beta naught, so that becomes beta naught sigma 1. And then we can factor out a beta 1 as well, minus beta 1. This becomes sigma just xi equals 0. Now we have these remaining sigmas, so we can come over here. Actually, I'll try not to stand in front of the camera here. Get out of the way here as best as I can. I'm sure my fat head's in the way. So this becomes, excuse me, actually we're eliminating the sigmas now. And actually let's do these down here just so you can see what we're doing. So then this is still y bar times n minus beta naught. The identity for this is just n, so this is just beta naught times n. The identity for this is, so it's still beta 1, and then it's times x bar times n equals 0. Now the nice thing is that all of these terms share an n. So if we divide out n into 0, we eliminate the n, and then we're just left with y bar minus beta naught minus beta 1 equals 0. We want to isolate beta naught to solve for that, and then we'll leverage that to actually get us to the Pearson form of the slope coefficient that was presented earlier in some of my videos for you. So all we have to do is add beta naught to the other side. So we that subtracted beta naught, we add over this side. Beta naught equals, and then it just equals, and I'm going to move this y bar over. So y bar minus beta 1 equals beta naught. So that this is beta naught. We're going to leverage that then when we work through solving for the slope. And that is our next step. And actually, I'm going to erase a lot of stuff because we are going to need space for this one. Always what you want to hear about these. We need to erase everything so that we have space. Luckily, it's a small whiteboard, so don't panic. My whiteboard is not huge, so it couldn't be that bad, right? Now, we're taking the partial derivative of f with respect to the slope coefficient beta 1. So that's our next step. We're going to write this out again. So that's sigma yi minus beta naught minus beta 1 xi squared. Make sure. This is going to start very similarly, where that 2 is going to come out front. So it's going to be equal to 2 times the summation of, and then also there is a negative here in this coefficient, so that negative is going to come out. But this xi cannot come out. So this is also an attached coefficient with the beta 1 value. So even though that's going to go to 1, we have this negative 1 we can pull out. We cannot pull out the index value, but that value will remain. And so we're going to account for that. Just put this out front, and then it's going to look identical to the rest of what we had in the last one. Beta 1 xi to the first power. So that's the only major difference now is we've got this xi out front. In the same way, when this is set equal to 0, we can get rid of that negative 2, so that makes our lives easier. So we get rid of that negative 2 because we're dividing it into 0. And now our next step will be, we want to take this beta naught. We actually want to apply our new identity that we created for that. So our new equation we have for our intercept, we have something we can actually, an identity that we can leverage. So this will come down here. This is going to be yi, but when I insert negative beta naught, these signs will flip. So it's going to be yi minus negative y bar plus beta 1. And I'm sorry, I forgot beta 1 x bar. There is an x bar attached to that. That was a mistake I made. So keep that in mind. There was a little boo-boo there. That we have beta 1 x bar, because that x bar remained from our our derivation of that. So not sure. I have to go back in the video and see where I made that error, but yeah, there is an x bar attached to that. That x bar did not go away because it was. It became, the identity became, we could factor out the negative beta naught and x bar, and then that then we multiplied by n and we were able to eliminate the n's, but we were left with a beta 1 x bar. Whereas the y bar just had an n attached to it and the beta naught just had an n attached to it. So those things were able to simplify a bit easier. Now, beta 1 plus beta 1 x bar minus beta 1 xi. Bear in mind these are not the same x's. They do not cancel. So you wouldn't want them to because then we would not be able to solve for beta 9. So that's then equal to 0. Then we're going to distribute this sigma xi, but I'm not going to do a full distribution. I'm going to distribute it into the y's. We'll separate those, and then we want to isolate the beta 1 values because we actually want to solve for beta 1, and so that's why I want to leave those unattached. So xi minus yi minus y bar, and then we have plus the summation of xi times beta 1 x bar minus beta 1 xi equals 0. So all I've done is just kind of separate those out. Nothing illegal there. So now we can factor out we're going to want to factor out a negative beta 1, and it'll become apparent why I'm doing this. So we're going to come down. This is actually going to become minus sigma xi. I'm sorry, not minus, just that. We're factoring out a negative beta 1. So negative beta 1 x bar. And then these terms will switch. So if I'm factoring out a minus beta 1 here, this becomes positive. If I'm factoring out a minus beta 1 here, the x bar becomes negative. So it becomes xi minus x bar. And then all of this is still remaining here on this side. And this all equals 0. Now that we have a minus beta 1, we want to derive the positive value of beta 1, so the easiest way to do that is just to move all of this junk over to the right-hand side. So we're going to end up with beta 1 sigma, oh, that's terrible, beta 1 sigma xi minus x bar equals sigma xi, again, kind of get out of the way here of the shot, times yi minus y bar. Then we just divide out this term. So it goes down here, so we're just dividing this out on both sides. Xi minus xi minus x bar. And that is what beta equals, or beta 1 equals. Now we're not done. This is usable, but it would add more unnecessary steps and actually make our lives more difficult in terms of the number crunching behind this. So we want to manipulate it now. We want to manipulate it to look like the, not the full Pearson correlation coefficient, but the Pearson slope coefficient. So the slope coefficient that comes out of the Pearson correlation coefficient. And again, if you want to reference some of my earlier videos on that, please do. So our target, we want to come up with a target equals sigma xi yi. Oh, no, I'm just copying what I have here. That's not what our target is. Our target is xi minus x bar times yi minus y bar, and then all of this over the summation of xi minus x bar squared. So that's where we want to go. And this This again, recall, this is just equal to the covariance over the variance of x, and it's the covariance of xy. So, and the n minus 1 terms that are normally attached to these two, they both have them, so both of their n minus terms actually just cancel each other out. And again, you could see a bit more of a detailed review in some of my earlier review videos if you're confused on that. So that's why we can call this covariance over variance of x. Now, first things first, we probably want to deal with the denominator first. I want this, I want to start with this value and make it look like this value. So I think, that's probably where we want to start. I'm going to FOIL this first. So this is the same thing when you square it as just xi minus x bar times xi minus x bar. And so we FOIL, and then that's going to end up equaling xi squared minus 2xi x bar plus x bar squared. And so that's what we end up with here. Then we're going to want to distribute the sigma. So this will be sigma xi squared minus, and I'm actually going to, we'll do this pedantically, never mind. Sigma 2 x bar xi plus sigma x bar squared. Now, as we're moving down this, we want this to, we want to use our identities to break this down even further. Notice though, I want to do something down here before we do. So this denominator, let's distribute the sigma xi in. So before we go any further with this, just real quick, I want to distribute that sigma xi into both terms. So we have sigma xi, and then that is multiplied by xi, and then we have minus sigma xi times x bar. So it's kind of close. I mean, you can tell that this is actually fairly close to that. And then if we simplify these even a little further, actually let me check my notes here before we just go jumping through all of this, the rest of this. Yeah, I do want to do it this way. So I'm going to go minus x bar. So we can factor out the constants, and we can combine these terms into x bar squared. So this just becomes, xi squared minus x bar times sigma xi. So now, why I do this, just so you know, because I'm going to jump into breaking these down into their identities. I do not want to break this down. That looks good. It looks like this. So we want to keep that, because it's getting us warmer, not colder. So that's what we're going to end up doing with that. So we have this xi squared, and then it's minus, we're going to pull out the 2x bar sigma xi plus x bar squared sigma, and then we're just left with a 1. So that's nice and easy there. Now with these, what we can do is we'll just take our identities. So this is going to become negative 2x bar. This is x bar times n plus x bar squared, and then this just becomes times n. So we're just leveraging the same identities we've been using. Then we have this sigma xi squared. Now this is cool, because these x bars are going to combine, so they're going to become x bar squared, 2 times x bar squared times n, plus x bar squared times n. Notice these are the same value. 2x bar squared times n, and that's a minus, plus x bar squared times n. So they'll actually just turn into, so this is going to drop down to something even easier to work with, xi squared minus x bar squared times n. Because again, these terms are the same. It's just I have -2 of one of them, and I have +1 of them. That gives me -1 of them. So now we want to break this back out, xi squared, and then we can break this out as x bar times n. This becomes sigma xi squared minus x bar. We reverse our identity. Sometimes it feels like you go back and forth in these things, but then all of a sudden you see, oh my goodness, this is the same thing as this. So we have now at least proved that our denominator is in fact equal to this. So that we can check that off. That's sort of the first step, and then we have to finish off with the numerator. And luckily I always start with the more painful one first in terms of time. So the numerator is a little easier to deal with. But I had basically just proven that now, in fact, I could take this x squared, break it down, and then make it look exactly like what we had in the denominator, such that we can now say that those denominators are equivalent. And I bet you can guess it, we'll be doing something similar with the numerators. But this time I'm going to go the other direction. So instead of starting with our Pearson slope coefficient here, we're going to be taking our existing beta 1 that we had solved for with the derivatives, and then we'll be trying to turn it into that instead. So down here we have, and actually I'll do this in black since we're coming the other way so you can see me going the other way here. We have the summation of, now in the numerator, xi. I want it to look like this. Xi minus x bar times yi minus y bar. We have yi minus y bar. So why don't we just subtract an x bar? That seems like it would get us closer. The only issue being, if we subtract that, because that did not originally exist in here, then we have to add it as well. So plus x bar. And then once we add it, then we can multiply this again by yi minus y bar. So I haven't done anything illegal within this parentheses. We just kind of expanded the parentheses out quite a bit and said, oh no, we could make it xi minus x bar, but we have to add that x bar back in. Now, this is pretty cool, because then our yi and y bar can just distribute to both of these terms. So treat this as one term attached with this, and this is the other term that this is going to attach to. So then this just becomes xi minus x bar times yi minus y bar initially. And then over here we still have this plus x bar times yi minus y bar. And this is all, the y's are sums, so let me actually cut that in there a little tighter. So I'll put a sum here so we can separate these out. Plus x bar summation. And I'm going to leave the x bar out because it doesn't need to be distributed in or incorporated under. Again, it's not an index term, so we can just pull it out. Now, with this, we want this to go away. So I'm going to distribute the summation yi minus the summation of y bar. This is an identity. This becomes y bar times n. We pull the y bar out. This just becomes sigma of 1. That becomes an identity. So then this is y bar times n minus y bar, and this identity is n, so that's times n. These two subtract, they equal 0. So if this term goes to 0, we multiply that by that x bar that we added in here, Well, that actually just solves it all for us, because this is going to equal 0. So we can wipe that out, and basically we're done. So then all that's saying is plus 0, so we've shown that, in fact, our numerators match. So this numerator is equivalent to that numerator. Hopefully you found this video useful. If you did, like, subscribe, all of that. I will, worst case scenario on the little boo-boo on the beta node, I'll leave something in the comments, or not in the comments, but in the description, and just make note of that, I guess, that I messed it up, depending on how bad of a boo-boo it was. But otherwise, I will see you guys next time. Thank you.